Illumination compositing for dark scenes. Let us look at the problem first. Consider a dark scene illuminated part by a moving light source. We propose a novel approach which would enable us to perform selective and sequential compositing of a scene under a moving light source. We assume no information about camera parameters, scene reflectance, and light source direction estimation. This application can be extended to real-world situations like international borders or prison surveillance, cave or mine exploration, special effects, etc. Here are the motivations and objectives. The primary motivation came from the observation of natural phenomena. One can think of someone removing the frost from a window to reveal the scene outside, scratching a car to reveal the details inside, or use radar to locate the target. Our application derives inspiration from all of this. The objectives behind the approach include selection of optimal number of appropriate video frames and composite them. Apart from this, we detect the path of the moving light and also determine the direction of the incident light source in planar scenes. We have uploaded a sample video we have captured for this application as a supplementary material. We use the flashlight as shown in this figure to illuminate the scene. This flashlight, which has a 3-degree cone, is commercially available. It produces no artifacts and generates circular or elliptical illumination region on a planar surface depending on its orientation. Let us look at the processing we perform on the frames of the captured video. We binarize each frame which lead to an image as shown at the top. We employ a morphological closing with a disk function to get the elliptical illuminated region which is shown in the middle figure. We perform canny edge detection to determine the outer boundary of this ellipse. This is shown in the bottom figure. We then use basic formula to find the centroid of the ellipse. After selecting the centroid of each frame, we calculate the average spread of each ellipse using the first formula. This is also illustrated using the figure shown. We select only those frames which satisfy the second formula. It conveys that the average spread of the two frames should be close enough to the distance between the centroids of their illumination region. We start with the first frame of the video and select the next frame which satisfies this criteria as the second frame. In this manner, we will have selected the minimum number of frames which span the entire path of the moving light source. After selecting appropriate frames, we employ exposure fusion by Mertens et al. 2007 to composite the frames. This method was primarily used to composite multi-exposure images. The proposed approach for solving this problem is as shown in this diagram. We take the video of the scene illuminated by a moving light source and recover the illumination pattern ellipse from the video frames. We then estimate the centroid and average spread of the ellipse corresponding to every frame. We select the appropriate video frames for compositing. The line joining the centroids provide the information about the light path on the scene. We perform compositing on the selected frames using exposure fusion. Here are the results. The thumbnails in the left show the frames of the video. The image on the right is the compositing result. This image shows the path of the moving light along with the composited image. The image on the right shows the partially illuminated scene and the associated path of the light source. For planar scenes, by determining the major and minor axes of the illumination pattern, one can determine the orientation of the light source with respect to the scene. This is shown in this figure. Here are the selected frames and the composited image corresponding to another planar scene. The scene shown here have objects with glossy surfaces and is also non-planar. This leads to a glare in the composited image. The glare can be avoided by having some knowledge of the scene reflectance. Otherwise, we are able to composite the frames of the video and obtain the illuminated image of the scene. Here is a complex non-planar scene in which the cable produces shadow on the wall. Since the shadow will be present at various locations of the wall in the video, the composited image has artifact. This artifact can be avoided by having a prior knowledge of the scene geometry. Here are another set of frames of a scene illuminated by a surveillance light. The composited image shows some artifact at the right top corner due to the movement of the insects. This can also be avoided by properly detecting the insects in each selected frame of the video. Now we shall see the conclusions. We have proposed a novel approach for compositing frames of a video which has a dark scene illuminated by a moving light source. This can be extended to determine the direction of the light source even for complex non-planar scenes. For non-planar scenes, scene modeling is required to achieve compositing without any artifacts. Thank you.